The topic of this video will be the ozonolysis of alkenes. Ozonolysis is another oxidative cleavage mechanism of alkenes. For example, treatment of this alkene with ozone followed by dimethyl sulfide produces a ketone and an aldehyde. Notice that unlike permanganate cleavage, we don't oxidize all of the carbon-hydrogen bonds, only the carbon-carbon double bond. This reaction uses ozone to oxidize the alkene. Ozone is most commonly drawn as a resonance hybrid between two contributors that help to spread the formal charge out over multiple oxygens. In the first step of the mechanism of this reaction, the pi bond is going to act like a nucleophile and attack the electrophile in ozone. The negatively charged oxygen of ozone is going to act as a nucleophile and tack back to form a cyclic intermediate, similar to those we've seen in the past. Except this will be a 5-membered ring because it involves all 3 oxygens of ozone as well as the 2 carbons of the alkene. This produces an unstable intermediate called the primary ozonide. This intermediate contains 2 peroxide linkages and is very unstable. It rapidly rearranges to cleave the carbon-carbon sigma bond still remaining. The rearrangement of the primary ozonide goes through another very unstable intermediate before becoming the ozonide, which is considerably more stable. The ozonide is considerably more stable than either of the previous intermediates, and the reaction pauses here until the introduction of the dimethyl sulfide. But let's pause for a moment and follow the carbons through this oxidative ozonolysis process. I will use color coding so that we can follow all of these carbons and oxygens throughout this process. Because none of the sigma bonds break in the first process, it's fairly easy to follow the carbons and oxygens from the alkene and ozone into the primary ozonide. In the next step, the carbon on the left, the red carbon, becomes the carbon that is double bonded to the oxygen with a positive charge. The oxygen with the positive charge is the red oxygen, and the oxygen with the negative charge is the blue oxygen. The other carbon that used to be involved in the alkene is the carbon of the aldehyde, and it is attached to the green oxygen. Following rearrangement into the ozonide, the red carbon is the carbon with the 2 carbon substituents, and the blue carbon is the other carbon that is involved in the cyclic ozonide. The red oxygen is still bound to the red carbon, and the blue oxygen is still bonded to the red oxygen, but is also now bonded to the blue carbon, leaving the green oxygen as the remaining unlabeled atom. Following formation of this ozonide, dimethyl sulfide is added to reduce the ozonide down to the ketone and the aldehyde. You don't need to know the mechanism of this step.